Good morning. Hello, everyone. I wanted to begin by thanking the organizers for inviting me to give this talk. It's been a while since we've had these in-person talks, and I'm very happy with the workshop. I was invited to give an experimental overview of medium response sensitive observables. I think we all know what we're going to be talking about, but just to set the stage, if we have a quark gluon plasma and we have a hard parton traveling through this quark gluon plasma, these jets or these hard partons will transfer some of their momenta to the medium, and well, this medium will respond. These medium partons will acquire additional momentum that will end up as a correlated energy with the jet, and this creates this wake and this depletion behind that wake. And after we end up with hadrons in our detectors and we run our subtraction algorithms, these subtraction algorithms do not and should not get rid of this correlated medium response. The average background gets subtracted, but this medium response effect is still encoded in our final state hadrons. And so this is precisely what we want to study, or at least what I want to highlight in this talk. So how do we go about studying this medium response? Well, first of all, we can try and do it by finding jets, as you see in this in my cartoon proof here. This medium response will be encoded inside the jet, and we can use this as a tool. Of course, the signal of the medium response in something like this will be overwhelmed by the actual by the signature from the hard parton and the shower. Something else that we can do is we can, for example, look at larger angles. We could do this with a larger radius jet. And so this is going to be, in a sense, the common theme, which is we look for where a jet is, and then we look at large angles from it. And so this is overall to set the stage. Why do we care about studying these medium? Oh, and by the way, of course, all these words on the bottom: correlated background, medium response, wake, recoils, Mach cone, jet-induced medium flow, back reaction. These are all different words to refer to the same underlying process or to some aspects of this process in the literature. Sometimes we see some of these words, sometimes we see different wording, but it all refers to the same underlying phenomenon. And why do we want to study this? Why do we care? Why don't we just try to avoid looking for it? Well, first of all, if we want to fully characterize the quark gluon plasma, we need to understand this aspect of it as well. In a recent conference, James was talking about, instead of using jets to understand the medium, also looking at it the other way around, using the medium properties to try and understand jets themselves. So if we want to have a better understanding of observables in the medium, that's another reason for understanding this medium response. The medium response encodes bulk properties of the quark gluon plasma. And you can see in this calculation, if we have a hard parton going up in the slide, in this first column, we can see that as we change the viscosity in the medium, the specific shape or the specific structure of this Mach cone differs. And similarly on the right, if we change the velocity of sound in the medium, this Mach cone also changes. So if we can really in detail do measurements or understand this medium response, we can use this information to further constrain properties of the bulk properties of the medium. And then finally, as was highlighted in yesterday's talk by Soren, the thermalization process, how fast is the jet energy thermalized in the medium, can also be studied by further constraining this medium response. So these are a few reasons why we want to understand this medium response better. There's a handful of theoretical models we have in this table. In the first in the different rows, we have, for example, in the first three cases, different frameworks. As we go down, there are some other models. And then as we go to the right in the columns, we have different ways to implement, different models to implement this medium response. We have these recoils that we heard a little bit about yesterday. We have this hydrodynamic response with source terms, deposited energy as perturbation, Boltzmann equation based, and then different frameworks or different models use different ways of implementing this medium response. And we're going to see a series of talks today about these some of these aspects. But the bottom line is that there are several ways of describing these, and there are some open questions. What's the right model for medium response? In these interactions, how perturbative or non-perturbative are these interactions? And how much do these recoiling partons thermalize? There are many other questions, and we would like to further use data to try and constrain and further understand this medium response. And so that's what I'm going to focus on. I'm going to be talking about specifically identifying experimental observables that show sensitivity to medium response. So where can we see this medium response effect? We were talking before about these jets going through the medium and acquiring this contribution from the medium response. So we can think that these jets get their substructure modified. So a way to look for medium response is to analyze modification of the substructure of these jets. We can also think of these medium response or this jet medium interaction taking energy away from the cone or depositing energy back into the cone. So we can also look for energy loss or energy redistribution. And then finally, we will see that we don't necessarily even need a jet. We just need to know where that jet was going and then look for the hadronic activity around that direction. So another way of doing this is by looking for a high PT trigger and then looking in the opposite direction to identify these effect of the medium response. And this is basically going to be the outline of my talk. First, I'm going to talk about some observables in terms of substructure modification. Then I'm going to talk about measurements of RAA and how these can show sensitivity to medium response. And then finally, I'm going to focus on these high PT triggers and hadronic activity in the backward direction. So let me begin with substructure modification. The classical example of the observable that probably has shown most sensitivity to medium response are these jet shapes. They describe how energy inside and outside jets is distributed in the radial direction. So what we do is we look in annuli around some direction and we add the PT in that region. And we have here on the right a measurement of these jet shapes by CMS. And so what we have is an overlay of different models. And down in the bottom, we have these three papers. Each one of these papers used the same data and then looked at the different models. So what I did here is I just put them all together. And so what we have is the distribution, the probability density function for these jet shapes in lead and in PP. The measurement by CMS would be these black markers. And then we can see different models. There's these coupled jet fluid model, which is the blue lines with and without the medium response. So with would be this solid line and without it would be this dashed line. We see the Martini prediction without recoil in this red dashed line and with recoil in this red solid line. And then we also have the hybrid model with and without this back reaction. And so we can see several things here. So first of all, you can see the large deviation in some cases of these models with and without the medium response. We can also see the fact that the models in some cases disagree among themselves. And then going back to what I said before, I grabbed these different theory predictions from different papers. Something that I want to come back to is that we should do a systematic study and look at all of these different models in a consistent way, not just look at some of them in some cases. In the next slide, I'll also show that. So, so before going there, just real quick, you can see that this is for jets of radius of 0.3, which is where this curve ends. And so, well, here we can see the purely the lead measurement. And so this is a similar measurement by CMS. This is also for R.3, which is this value that I have with this dashed line. And so again, this is only the lead density. We can see that the data, so that the cone of the jet ends there, but we can still look outside. And so we have the measurement in black. We have this coupled jet fluid model prediction in red. And then in this specific plot, we can see the breakdown of the different components. And so, for example, the shower part is this blue curve. We can see that inside the jet cone, it dominates. But as we move outside the jet cone, the contribution goes down, and what dominates is the contribution from this yellow curve, which is the medium response. So this is just an example of probably, again, as I said before, one of the substructure observables that has shown more sensitivity to medium response. It's not the only one. Marta talked about this angle between different jet axes. So we run our clustering algorithms, and we put together jets, and we can see where these jets are pointing. We can take these standard jet direction and compare it, for example, to the jet direction after we groom some of these soft wide angle radiation. We can also take these winner-take-all axes, which is put together by reclustering the jet with the Cambridge-Aachen algorithm, and then in the recombination step, we add the PT of the two branches, but follow the direction of the hardest one. And then we can measure the angle between a pair of these axes. As I said, well, so what you see here is the prediction from Joule with and without recoil. So recoils on would be red, recoils off would be blue. We have in this distribution the angle between the winner take all and the groomed axes. And then in this first plot, we have R.2 and R.4. So small r with grooming, large R with grooming. This medium response is soft wide angle radiation in a sense. So if we groom, we are getting rid of it. And what you can see here is that we don't have sensitivity to this medium response in these two cases. Something else that we can do is we can, well, not groom. So here on the bottom, you can see small r, no grooming, and we still see very little medium response sensitivity. So we have small r with grooming, large R with grooming, small r, no grooming. If we look at large R without grooming, then we start to see some more sensitivity to this medium response effect. This is a recent measurement from Alice. I'm not going to go in details about these plots. Marta showed them, and Laura will also talk a little bit about them tomorrow. The main point that I wanted to make here is that when we look, as I said, and as I showed with the jewel case, when we look at small radii, we don't see this sensitivity to medium response. As we go larger in radius, you can see here the distribution for this angle variable. We have the result from R.4 in yellow, the result from R.2 in blue. We don't have the PP baseline. This is only lead. And so this is a very high PT for Alice. We have without grooming on the left, with grooming on the right. And what we can see is basically the same thing that I showed with the jewel predictions before, which is when we go to the case with more grooming, we start to see very good agreement in the models with and without recoils. When there's no grooming, then we start at large angle, we start to see deviations in these models. As I said before, it's not as much sensitivity to this medium response as we see in the jet shapes, but we can do a very good precision measurement in this case, and we can start to see the disagreement between the models and the data. So this can also be used to test this medium response. There are some other substructure observables as well that show this sensitivity. But so let me move on to this jet energy loss or jet energy redistribution. I'm going to focus on RAA measurements. And so we've all seen this measurement from CMS. We have the RAA for a jet of a given radius divided by the RAA for R.2 as a function of the jet radius. This is for central let events in these high PT classes or bins. And the measurement is these red points that we see here. We see that it's flat as we go to the right, as we go high in jet radius. And the data shows little sensitivity to R. These points, to some extent, to some cancellation of different effects. And then we can look at what different models predict. And so, for example, if we look at Joule here, again, with and without recoils, as we would expect, this model predicts that when one goes higher in jet radius, we start to see larger effects from this medium response. The same data compared to some other models is shown here. And so what we can see is, for example, the hybrid model with and without the wake, the LBT model with these showers or the showers and medium response. And what we can see is that, again, as I said, the data is flat. The models in many cases are not flat. However, we can see that some models do show agreement with the data. The main issue here is that if we look at the absolute RAA and not the ratios, we start to see that those models that agreed in the ratio are not agreeing in the RAA. So we have to be careful with that when we interpret why some of these models do agree and why sometimes they don't. Here we can see another measurement for RAA, and in the coupled jet fluid model, in the case when there's no medium response, which are all these dashed lines, what we see is that as we go up in radius, the model predicts that there's no strong cone size dependence. When the medium response is turned on, what we see is that as we go up in radius, there's more sensitivity to this medium response. And then finally, this is a recent measurement by Alice. I'm showing, by the way, in all these slides, the cases in which these results were premiered for quark matter. And so without going into too much details, the common theme here is that as we go up in jet radius, some of these models predict higher sensitivity to medium response. And then in my last 10 minutes, I'm gonna talk a little bit about these hadrons recoiling from a high PT trigger. There's this measurement from Chris McGinn that was shown in quark matter, in which we have this semi-inclusive yield of hadrons recoiling from a Z. And so what you can see here is this IAA, which is this ratio of the yield in lead over PP. The data is shown as these markers. And what we have here is for the different PT, for the different PT for the Z, we have the data and markers, and then we have the hybrid model with and without the wake. With the wake would be the cases that, so first of all, at high PT, both models agree. As we go low in PT, we see this uprise that is seen in the data, and it's seen in the hybrid model when we have this medium response turned on. When it is turned off, we see this behavior that continues to go down. A similar measurement was done in CMS. We can see here these similar ratio. You can see that qualitatively, we see the exact same trend. As we go up, low in PT, we see this uprise. And we can see also, there are different models here, but focusing in the case in which we can see the effect of the wake, which is the hybrid model, we can see that once again, there's some qualitative agreement between these trends when the wake is turned on, and we don't see it when the wake is turned off. As I said, this is qualitative agreement for this specific case. There's some tension, but the main features are captured. And there's also this Z-tag fragmentation function. Of course, all these information is correlated. This is not a separate thing, but the common theme is that, again, we see these trends that are qualitatively similar when the medium response is present. There's also these acouplinarity between the high PT trigger and the hadronic activity in the opposite direction. And well, without reading too many details into it, we can also see that the models in which we see these medium response on and off shows some differences. So another handle for looking at these effects. And then finally, I'm not going to talk too much about this because Peter will describe these in detail. But there was also this recent measurement by Alice in which we looked at the semi-inclusive yield of a jet recoiling against a high PT hadron. I'm not going to talk about these, but there were this subtraction method was developed to get rid of the uncorrelated background. And after taking into account these IAA ratio was also constructed. And we can see here this IAA as a function of PT. And again, qualitatively, we see this similar trend. At this point, this has not been compared directly to models, except for this prediction from Jetscape. But specifically in the low PT region, this is not being compared. But thinking about the few slides that I showed before, in which we looked at this hadronic activity recoiling from a high PT hadron, we saw that this uprise was also due to medium response. And this is very much off the press. So I got this new plot from Danny yesterday. And so this is calculated with the hybrid model specifically for the kinematics of these Alice measurements. And qualitatively, once again, we see that when the wake is turned on or off, this uprise trend at low PT is very different in the model. So basically what I have done is I have given you a lot of information about different experimental observables that show sensitivity to medium response. The caveat, of course, is that the sensitivity is based on the fact that we are looking at models that predict these different behavior. And so how do we move forward? What do we do with this? Well, this is my personal take as an experimentalist. Of course, we can talk about different ways of proceeding. But I think that besides the further improvement of the models that we have, something that we can do is identify more medium response sensitive observables. We were chatting yesterday about this study that James and Mateusz did, in which, for example, machine learning was used to classify observables as more or less sensitivity to jet quenching. In principle, one could do something similar to construct observables that are IRC safe, but still that quantifies the amount of information that we can extract in terms of medium response. As I said before, I think we also need to do a systematic study of these medium response models. What I see in the literature is that sometimes the models disagree among themselves. Sometimes the models are compared very independently. So I think we should also go in more detail about that. And something else that we can do in parallel is we can develop a parameterized model that hopefully that parameterization includes physics aspects in it. And we can do, for example, Bayesian inference on the data that we have across all these observables, and we can try and constrain a model for this medium response. So that's all what I wanted to talk about today. In summary, basically a detailed description of these jet-induced medium responses necessary if we want to fully understand the quark-gluon plasma. These medium response can be sensitive to bulk properties of the quark-gluon plasma and to the thermalization process. I tried to put together a list of experimental observables that have exhibited the sensitivity to medium response, again, as implemented in different models. In many cases, the models only agree qualitatively with the data. So I think we need to understand that better and use the data that we have, which I said in many cases is very precise data, to further constrain and understand these models. And so what I think we should do is both focus on observables that don't exhibit these medium response to make sure that we understand the models when this effect is not too large. And simultaneously, we don't have to do this in series. I think we can do it in parallel, go to the corners of phase space where this medium response is larger, and then try to also understand what's going on in there. And then finally, something that I did not mention at all, but I wanted to put it out as a disclaimer, is that we still need to be careful about some other processes that can mimic this medium response. For example, the standard example is medium-induced wide-angle radiation. So we just need to be careful about the fact that there are some other competing effects as well. And that's all I wanted to present today. Thank you.
I've been thinking about this question for the last 10 minutes of your talk, and then your very last bullet there really addresses it, or leads to that question. In the end, most of these observables, what we really see is that energy shows up or is missing in some angular or momentum regions in heavy ion collisions compared to PP. And I think in principle, based on the data, just based on that observation, I think it is extremely difficult to decide how did that energy get there or why did it disappear from that particular region. Because in the end, energy momentum are conserved. You're just seeing a redistribution. And I don't necessarily think that the observables that we have so far particularly sensitive to how the energy was redistributed in a model-independent way. For those of you who have been in the field longer, my recollection is that this paradigm shift to really talking confidently about medium response happened at the time of Quark Meta 2017. And I was really surprised by that because there really wasn't any qualitatively new data. This was more sort of a collective effect in the theory community rather than any collective effect that was seen in the data. And I'm still not satisfied that we have ruled out wide-angle radiation or some violent modification of the jet structure that is not actually related to the energy flowing through the medium in the end. And I think this is a sufficiently important question that sort of a crisp experimental proof of which of these mechanisms is correct is desirable.
Just wanted to maybe give the word a bit to the back of the room. We'll come back to you. No, sorry. But yeah, is there any, because we want to just try to involve everyone here. Anyone in the back here want to comment? I see you kind of counting in front. Yeah. Okay. No, seriously, yeah. Mateo, your turn. No, okay, please.
Yeah, I completely agree with Quinter. I actually put it more strongly. I think even in principle, there is no way experimentally to distinguish shower modifications from medium response. I think it's entirely, well, I'm going to qualify that in a second, but I think at the moment with what we're measuring, it's entirely in the model space. I don't think experimentally we have a way to distinguish. Now, there may be in principle, and Ray and I were chatting on the way in, there may be in principle a way to discriminate if you can identify conserved quantities and identify what having flavor. If you can look at, for instance, and this is a process that Norris talked about, on the first day, glucose to CC bar, that's a known process in QCD, the correlation is known in vacuum. You can study that correlation and how the CC bar pair as an object is related to the jet axis. And then how the C and the C bar are themselves correlated, I think perhaps in pure conjecture, one may be able to distinguish shower modification from the charm being dragged by the medium. That's just pure speculation. There may be in principle observables that can pull these apart, but I don't think anything that we have today. So, President of Ray's talk, and he's pretty much said the same. I don't think any of the observables we have today are capable of doing that. I think it's perhaps not unresolvable in principle, but it's certainly a future measurement.
So Yassine, then Chris on Zoom, and then Martin.
Yeah, I think your last point there is very important. The medium response from model perspective, right, is very sensitive to how you model the shower, right? So you might get more medium response or less given the same modeling of medium response if you change the shower. So what you're probing in the model, medium response, you're also probing how this medium response was generated in the first place with the certain modeling. So we have to be careful with that. So it's very important to first test region of phase space where medium response is not so important, so that we are confident that the shower is well understood to a certain degree, and then go after medium response where we could be confident that we can measure medium response as a reaction or a consequence of a certain part of the shower that is understood first. So I think that's important. And just one last point, looking at the variation in the RAA, this double ratio between width of model, between with and without information, this should alert us. Right? And that observable is supposed to be the observable that we understood, we thought we understood. That's the observable that shows the strongest, variation, to and sensitivity in models. So we should really think carefully about what we want to achieve.
So if you want to respond,
Well, I mean, so I think I guess these have been more comments, and I don't have any disagreement with that. As I also pointed out in this double ratio, we see in some cases, even in the cases in which we see agreement, we then go to RAA by itself, and the models still disagree with the data. So yeah, I guess again, I don't disagree with anything of what has been said.
So Chris, on Zoom, you can go ahead.
Hi, yeah, maybe a clarification from Peter. Were you conjecturing that the CC bar would be a model independent test of medium response?
Insofar as it's a conjecture, yes, but it's certainly not approved.
Okay, well, I mean, I've found saying model dependent test of medium response very dissatisfying. So that's interesting. And then I guess for the speaker, are there other candidates for possible model independent tests of medium response that you have in mind, possibly?
So for what I have seen so far, in the literature, I don't have anything specific in mind, but what I have seen is that the tests or the level of sensitivity is always tied to some model, and as has been said here, that can be in a sense problematic, and we need to be careful about how to interpret those models also, as we discussed yesterday. And I did not talk about this in detail, and I did not think about this in too much detail, but again, we were chatting yesterday about this idea of designing observables, trying to quantify and trying to maximize the amount of information of some given type, and constraints to make these observables still calculable. And so this is something that that could be potentially explored.
Yeah, I would like to follow up a bit on this first comment or discussion about distinguishing basically the large angular variation and the medium response. There is one observable that I have had in mind for quite some time, and it's difficult measurement to be done with Atlas. Maybe that's why I'm saying it. Maybe it would be great for Alice. Basically, trying to do some a chemistry measurement of this of these soft particles that we see within the jet or outside the jet. So basically measuring a K-shorts, lambda, something like that, basically the soft fragments, and checking whether they are consistent more with what we know is the composition of the medium or what is part of the jet.
Okay, we have time for one last. You want to say
Well, we have made some of the studies for lambdas and k zeros, and let's say only on the PT spectrum, lambda of k zeros, which are outside the jets, look similar to the underlying event. Those that they are inside the jets, they look consistent with some modeling of fragmentation. The jury is still out. We need more data to do this better. But yeah.
Okay, I think we have time for one last question before we have to move on. We'll be quicker questions and comments for the discussion session.
Yeah, I just would like to comment that we have already learned about from experimental data, and actually the ball is in the series side. So, for example, we see that in our data, the jewel doesn't describe the data, right? So because the median response is too correlated with the half growth, right? And I also wonder about your comment on what we have learned. And what I also observed is that the hybrid model have a too soft median response and rate of 2 to 4 GeV particles. For example, those treating like that. So I think I wonder, can you actually try to compare what would be the direction of getting more experimental observables, or is there any way we spend more time to help our theorists, friends, to really investigate systematically what has already been measured, so that we can make more progress?
Yeah, and as I said before, well, we saw it, right? I was emphasizing as much as I could that there's a qualitative agreement in the trends, but not quantitative agreement. And I think the data that we have could be used to further understand why in some cases, like Joule goes in one direction, and in some cases it goes in the opposite direction. Try to further constrain that. As I said, I think we have precise data that we can use for that.
Sorry to the audience on Zoom. I think we had the mic turned off here in the front. Do you hear us well now?
We tested before and someone responded that they could hear us.
Okay. And you hear us well here as well, right?